recording?
Yes.
Awesome, sweet. So let's talk about designing large-scale systems for the web. So you're making a web application for your startup or your business, and it probably kind of looks like this. You have clients, and they use the internet to talk to your server. It's pretty simple, right? Actually, no, it's very quickly going to look like this because you're a fast-growing startup, and you're going to get a lot of users really quickly. And also, because you're a fast-growing startup, you're writing bad code, so your servers are also dying all the time, and you have to deal with that fact. So, this is very real. Look at this terrifying chart. Imagine being the engineer that has to deal with the fact that in this 6-month period, you have 6x user growth. How do you handle that load? You can't just make your code 6 times faster in every way and avoid all bottlenecks. That's really hard. What if you're ingesting gigabytes of data per user every day because you're tracking everything they do? What if you're Google and everyone stores their emails in Gmail, all 1 billion users of Gmail, and they all take a gigabyte each? That's a lot of data. You certainly can't put that on a single machine. What if, okay, is Ethereum working? See, latency is unacceptable. You can't do that, okay? After 3 seconds, you lose 40% of your users, and then every second after that is another 7%. Okay, your server has to be fast. You can't just eventually serve them the right thing. You have to do it choppy and quick. So how do we solve these issues? Well, I don't really know. This is a really hard topic, and a lot of people have talked about it. But I can share some cool things that I've learned about it. So first is let's talk about the different types of scaling you can do. You can scale vertically or you can scale horizontally. Now vertically is really easy. You have your code, it's running on your server. Oh, you got too many users? Okay, just make your server twice as powerful. Give it twice as much RAM, twice as much CPU, twice as much SSDs. Problem solved. You didn't have to change any code, but the problem is you have a single point of failure because you only got one server, and to upgrade it, you kind of have to take it down while you plug in the RAM stakes. So it's not really a long-term solution. You can, in fact, get pretty far with vertical scaling. You can double the size of your computer, give it twice as much power and RAM and stuff like that, and it'll only cost twice as much, but only up to a certain point. And then you're doing expensive mainframes with specialists and all of that. So instead, we do horizontal scalability. You don't have a single point of failure. What else is there? It's cheaper in the long run, and you can add more bandwidth and capacity on the fly. But how do you get your clients to know about the fact that you have a bunch of servers? Do you have 10 domain names and the users just pick a random number like Facebook10.com? No. Do you redirect them? Not really. What you do is you instead have a load balancer. So all your clients will instead talk to a load balancer. And that will actually get the server, we'll pick a server, the one with the least load, and get the server to handle the request from your client. Now, this is pretty cool. Unfortunately, it's also a single point of failure because if your load balancer goes down, everything else goes down as well. So you also want multiple load balancers, and then things start getting really complicated. One cool thing you can do with load balancers is you can do multi-region load balancing. So what if Amazon US East goes down? That's half the internet. Well, because you have a global load balancer, you can just reroute all that traffic to European servers or US West servers. That's pretty cool. I mean, your stuff will be slower, but at least it won't be down. Another technique often used is caching. So say you're Imgur and you host images. Now most of your images get very few views, but some of them go viral and they have very spiky load, which means they get thousands times more users and you get 1,000 requests per second for an image. Well, it would really suck if all of your servers were just duplicating all the work of serving that image all the time. You'd be getting hammered. So instead you have a cache, because there's only going to be a dozen maybe images going viral at one time. You can have a small cache that very quickly serves back data. You can reduce how much load you have on your servers, increase page load times, and also there's some nice properties where your database load is more uniform, which is good for them. What about this thing where, say you're in Chile, and you want to talk to this server in Germany, and this is a really long round trip. So if you're this German company, you might hire a content delivery network, a CDN. You might have heard of a company called CloudFront, to serve data for you. So CloudFront will put servers throughout the world, so that when users in Chile want to get your web page, they just talk to the Brazilian sort of copy of your code. Unfortunately, this doesn't work for dynamic content, like web pages where you log in and stuff. But for things like photos and videos and raw HTML files, things that are always the same, CDNs are really useful. Did I skip a slide? No, I didn't. So now we're going to talk about databases. databases are really important because usually web servers don't actually maintain state. Like they don't like change any information inside of them. What they do is they instead talk to the database and say, hey, edit these records. So databases are stateful, which means it's a lot harder to scale them than web servers. Because you can just kind of add more web servers. You can't just add more databases because you need like a single copy of like the truth about the world. By the way, this is what a database looks like on the inside, if you weren't aware. So one of the techniques that's quite common is called primary replica, also known as master-slave. Bad terminology, I know. But anyways, the idea here is that most of the time, for most applications, you're going to be doing a lot more reading than you're going to be doing writing. People will be requesting web pages, but very rarely will they be editing data. So you can have a single source of truth, which is your primary, and then you can replicate the data that's there into other databases running on other machines. And if a client wants to read, they can read from any of your instances. But if a client wants to write, they have to talk to your primary. Now, this does mean that your replicas are going to be slightly out of date, but that's just a problem that you have to deal with. Another technique is federation. So you can split up your database into sort of logical components that can run on separate instances. So your forums, perhaps, if they get hammered, they don't really, like the database that handles your forums doesn't also have to be the database that handles your users and your products. So instead, you can sort of split up the load like that based on like logical components. Another thing you can do is called sharding. So the idea here is that you can partition your data into different like disjoint components so that your application asks your load balancer for some like, for the user atom, like I want his deets. And then like the load balancer will redirect that to the database responsible for the users with the first names that start from A to C. This means you can have many more machines serving the same amount of requests, and you can split up the data. And it's pretty cool. That's enough about databases. There's this other thing. So suppose you're Twitter, you're a Twitter user, and you have 1 million followers, and you send out a tweet. Now, like maybe half of your followers, 500,000 of them, have like a setup such that when you tweet, they receive an email about it, or they receive a push notification. Now, if I sent the request to send the tweet, and it went to the web server, and then the web server sent out those 500,000 push notifications and emails, well, that would be really slow. That actually takes like forever. And it would really suck if you tweeted, and then you had to wait like 10 minutes while it did the processing, and then it returned, by the way, tweet sent successfully. Instead, your web server receives the request, and then it puts a message in a queue, like a job, that's saying like, hey, we need to send out these 500,000 push notifications and emails. Later, at some point, a pool of workers, which is like just servers, will read the messages from the queue, and then we'll send out the relevant push notifications and the relevant emails. And eventually, your push notifications will be delivered. So when you tweet, like people are getting instant live notifications. They might get them in 5 minutes, and 10 minutes, maybe 30 seconds. This is called asynchronous processing. So how am I doing on time, by the way?
You're good.
Okay, cool. So one thing that I enjoy doing is pick a service that I find online, maybe something simple or maybe something complicated, and think about how I would design it to be scalable. So like something like bit.ly, which is a link shortener. So you need to have it be high availability. You should handle like maybe 10,000 requests per second. Now, here's the thing. Bit.ly doesn't actually do 10,000 requests per second. It averages about 1,000 requests per second. But bit.ly usage is not constant. It spikes. So at peak, they might be handling this much. This happens for a lot of applications. If you're like Salesforce, like the vast majority of your usage is going to peak during like American business hours. And then in the middle of the night, you're going to have very little usage. So that means you want to save money when you're not receiving enough load. So like it's cool if you have 100 servers running to serve people at peak times, but you don't want 100 servers running at 4 a.m. when no one's using your service. That's a lot of money. And then as I mentioned, you'll have a 10-to-1 read-write ratio, and you have some constraint on your latency. But I'm not actually going to go over how this is designed. Instead, let's talk about another problem. This is, I guess, more complicated. So you can see how things might get pretty spicy. So user posts a tweet. The service pushes the tweet to the followers using push notifications and stuff like that. We talked about that a little bit earlier. The user can view their timeline, which is things they've posted, and this has to instantly update. You tweet, and then it instantly shows you that you made this tweet. You can also view your home timeline, which shows activity from other users, and this also has to be fast. If one of your buddies who you follow, or someone you follow who you follow, sends a tweet, the calculation has to come in, and it has to show you this new tweet, like fast. And you also have search across like all of Twitter using like hashtags. And this also has to rapidly update. Because when you search for tweets, you want to see the latest things. Like if there's an earthquake happening, you don't want to hear about an earthquake that happened in 2006. You want to hear about the earthquake tremors that you just felt. That means you're like updating these things really fast. And also, as is often the case, you have high availability. That means your things don't go down. So that's what this sort of diagram would look like at a high level. And this is what it would look like in more detail. I can talk about it like more specifically, or I could just end the talk here for questions.